Hello, everyone, and thank you for joining the Rutgers Geology Museum's Ask a Geologist web series. So today we have Dr. Don Monteverde from Rutgers University. He is an adjunct professor in the Rutgers Department of Earth and Planetary Sciences. Today he will be speaking to us about geologic maps. So without further ado, Don, go ahead and take it away.
Okay, as described, I am affiliated with Rutgers University. Uh, so beginning, they wanted me to show some of the things about myself. I grew up in Bergen County, New Jersey. I really didn't know much about geology until I went to college, and that's where I discovered geology as a major. These pictures you can see show my varied experience in that this lower picture, that's in Alaska. I did field mapping, and I also lived in Africa for 2 years doing mineral exploration. So I basically have a slightly different track on how I arrived to where I am now. Many of the previous speakers you've had have gone from undergraduate school to graduate school, eventually getting either a master's or a PhD, and then staying in academia and moving around. I started differently in that I graduated from my four-year university, and then I went out and worked. So for 4 years, I was either working at oil rigs in Texas, mineral exploration in Colorado, Wyoming, and eventually I joined the Peace Corps as a geologist, where I lived in Burkina Faso for 2 years looking for base and precious metals. Then I came back and decided I love geology. I want to earn a master's. I did that. Then I had my full-time job at the New Jersey Geological Survey, which I'm still working at. I've been there for over 30 years. And at one point, I decided I want to earn a PhD. I'm more curious. So I entered as a part-time student at Rutgers University, where it took me a while, but I finally did get a PhD in my 50s. And basically what I'm trying to say is you're never too young or you're never too old to stop learning. We learn all the time, and don't be afraid, even if you're older, if you want an advanced degree to learn more, to do it. Also, as you can see, I went through my photos and I have more photos of rocks than my kids. Hopefully my kids are not here listening to this. So geological maps. What are the geological maps? And basically, you can read the text. I won't read it to you, but they basically explain what the geology is of the given area. And they could be just what type of rocks they are. They could be where are mines. They could be where's sinkholes. They could be any type of thing that you want. So if you're making a geological map, you really want it to cover what you want to know. And so it's basically, in some ways, it's a historical map of what happened to the Earth way before we arrived here. So that's basically what I consider a geological map. And just so you know, the backgrounds for a lot of my slides here are geological maps that I was involved with making with some of the people that I work with. So as we can see, once again, reading that the first geological maps were resource maps. If you think there's a famous line, if you can't farm it, you have to mine it. So if you think back in historical times where people were looking for arrowheads, people were looking for iron mines for different things. These were some of the earliest maps, geological maps. So they were resources maps. It wasn't until like the 1800s that all of a sudden we started having a lot of national maps. So as near as I can find, the oldest geological map is this one here. It's 1150 BC. It's from Egypt. And this was mainly showing different types of rocks, but the main thing, it was showing where they had a gold mine. So if you look at, this is the entire data. This is their entire map that was put together by these people. If you want to learn about it, here's the resource. You can investigate it. And if this is a blow up of this section right here. And taking a quick read of their paper, I think up here is where the gold mine was that they were trying to track and figure out. But you can see that they're tracking different types of geology through this map. So geological maps have been known for a long, long time, much longer than I ever thought through. But as I said, this is the oldest map. One of the more recent maps, 1850, that's recent. This is one of the first country maps, and this was done by a gentleman named William Strata Smith. And he was a parson, if I'm not a parson, if I'm not mistaken. So he did this on the side, and one of the things that he used was fossils. He was able to identify the units by their fossil content, and this I believe predated Darwin. So he was be able to use these to identify the different types of rocks. He did his map at the time that a lot of canals were being built in the UK. So there was a lot of exposure. And this was also just when the Industrial Revolution was starting. So coal was a big desire. And so a lot of people were asking him, where could we find coal? If I have coal on my land, can I make money? So he did it more as a scientific endeavor, but the geology was more applied economics. And Charles Darwin, we all know he came up with a theory of evolution, but he was also involved with geology. And you can see this is his cross-section. A cross-section in a geological map is a slice into the earth where the scientist makes a interpretation of what he thinks happens inside the earth with the rocks. So here's Charles Darwin. You can see this is about 15 years later, and this is South America. And if you look at this color, once again, this end stitches with this end, and this end stitches with that end. So it's one huge piece. If you look at this color here, I believe he's mapping this here. I'm not sure exactly where it was, but just by matching the colors, I believe that's where it is. So this is the southern tip of South America, where Darwin did his work. So even though he did evolution, he was also interested in geology. A lot of the early scientists didn't really just focus on one thing, they focused on many different aspects of science. This is a famous map in the US. It's 1944 by Harold Fiske. Once again, here's the reference. You can go there and get this entire thing. And if we look here, this is the Mississippi River. Notice how it has a lot of bends in it, meanders we call it. And this map, it's showing the evolution of the Mississippi River in that if we look at this, it looks like this branch is cutting off this part of the Mississippi River, and eventually it will completely cut off, and this will be what we call an oxbow lake. So what he mapped here are all these oxbow lakes all throughout the area, and to me, this is a true work of art with science. So here he's color coding by age, so this is the same as this, that, and he's being able to do it by laying it on top of one another. So this is a very famous geological map. And if you ever fly from the East Coast and you have a layover in Dallas-Fort Worth Airport, you fly over the Mississippi River. And this is a Google Earth image. And here you can see where all these oxbow lakes are that Fiske mapped. So at one time, the Mississippi River was way over here. So this is the natural evolution of a meandering river. And the other interesting thing is this is the current Mississippi River right here. And if we look at this sharp line here, that's the state boundary between Mississippi here and Arkansas here. And what you can see is they used to use the Mississippi River as a boundary, but the Mississippi River evolved. So now you have Arkansas on the Mississippi side of the river, and here you have Mississippi on the Arkansas side of the river. So this is showing you how Frisk was mapping these things and how the river has morphed, and more importantly, the river is a lousy boundary between states because it evolves. And we do geology all over the place, including in other planets. This is a pretty recent map of Mars that was put out by the USGS. The USGS is the US Geological Survey. They're a really fantastic reference for geological maps. So these are all color coded by types of rocks, ages of rocks. We'll go into this in a little bit. And they're even doing this on Pluto. I just happened to find this as I was putting my slides together earlier in the week, how by one of the probes shot by Pluto a couple years ago, and now they're trying to get from the photos and other methods of taking data, they're trying to come up with geological maps so they can also map Pluto, which was at one time our farthest planet. Now it's called a dwarf planet. So we're doing this everywhere. And if we want to talk about a geological map, this is one from New Jersey, where I currently work, and I was actually involved in this map. So the map base is what we call a topo map. So the topo map shows elevation, and we use those as our basic map. And I believe I wrote down the distances, but I can't find them. So I believe this is about 6 miles here. This is about 10 miles there. So you can get an idea of the map. But this is a common general geological map. What's the geology? What can we find at the surface? What could we expect to find at depth? So we have all this pieces. So the first thing we have, we're going to blow up this. And this is a description of the map units. So each one of these colors is a different map. And this is telling you what the map is, what we call it, if we have the age of it. Like this thing right here, that's a diabase. The age is low Jurassic, and it describes what the unit is. So somebody can take this map, go out there and look at a rock and see, does it match this? Does it match that? What does it match? With geology, we have names for all the different units. So we can describe them in literature. The next thing is we're going down here. This is a correlation of units. So this is showing you the age of each unit. Once again, it's the same colors. So this here, which I know is the Triassic Stockton Formation, is on the map right here. This is the Lakatong, which is all this gray unit. There's our diabase again. The J is Jurassic in age. This is Triassic in age. So this is a way to see what the ages of these are. If you look at all these are very recent. Holocene's only 10,000 years ago. So this is a modern river that can overflow at times and deposit sand and gravel on the uplands, so to speak. So we're showing that also. And last but not least is this. If we look at this line and we slice the map and open it up, this is what we think is inside the Earth. So just so you understand, from about here to here is 4,000 feet. And a lot of this is predicted because we get data. So we use this because it's just like, I don't know, when I was a kid, you'd get invited to these birthday parties, and there'd always be a birthday cake. The birthday cake would always have icing on it. But inside the cake, commonly there was a yellow, I don't know what it was, but I didn't like it. So I was just, oh man, I wonder if that's in the cake. I would never know until they cut it. So this is this is a slice. Think of this as a cake slice from this geological map. So if you think about geological maps, this is just a puzzle. Geological mapping is a puzzle. So when I was a kid, I think most kids like puzzles. They like putting things together, matching pieces. And this happens to be, you can see it's an 1830 map of Southeast England. I picked this one because it already has puzzle pieces. So if you think about geological maps, Most of them were missing the pieces. If you buy a puzzle at a flea market or something like that, a garage sale, you don't know if all the pieces will be there. So that's what a geological map is. We don't see everything. Sometimes there's a lot of foliage, there's plants, there's buildings, there's roads. We can't see the geology there. So using our geological knowledge, we have to fill in these gaps with what we think is there. But it's, once again, what we think is there based on our geological knowledge of these areas. So for this map, let's look at this map. You can see many different colors. You can see most of the units are going in this direction. So how do I know that? How did I put that together? Well, as any geologist, you have to go in the field and collect data. So this is where I went in the field to collect data. These are my data points and my co-author's data points. So one or both of us visited every single one of these sites, and we collected data with a compass to see how were the beds laying. So these are the areas that we know what the geology is. So if you look at all the other areas, there's nothing there. So for most of this map, we have no data there, but we're using our geological knowledge. Now, we know from taking compass readings that most of these layers are trending in this direction. So if I accentuate that, we really know this much. So we're kind of filling in more of the map because we have a knowledge of the map. But still, there's a great deal that we don't have. What comes in exceedingly handy, I'll show you more of this, is LiDAR. LiDAR is a new thing that, well, it's fairly new, which is basically lasers in airplanes taking laser data from the land surface to see elevations. And some of these elevation models have an error of 1 foot. So they're really, really detailed. So this, if you look, you can see a box right here. This box is the same as this map. So here we can see that there are high ridges trending in this direction, and we can correlate those ridges with some of our data. You can't see it on this map, unfortunately, but there's a data point right there, I believe. There's data here. And we can see that these ridges correlate with these dark green units. So that allows us with LiDAR to fill in a lot of the unknown with data. Once again, we have to field check this. We can't just accept it. We have to look at this. Let's go out there. This is over here. Let's go out there and see, is this green unit, which I know myself it's a gray bed. Most of this, the color of the rocks mostly are red. So we use as much data as we can to fill in as much as we can, but we never get everything. If you look outside right now on the East Coast, all I see is green. This is not the time to map. The time to map is in the winter when all the foliage the leaves are off the trees, the ground foliage is basically dead, and you can see the rocks. If you go out the west where it's very arid, I just flew from California recently, going to Nevada, there's almost no foliation. There's a lot more rocks exposed, making it a little bit easier to create a map and interpret the map. So what do I carry when I go out in the field? One, I carry maps because I have to know where the heck I'm going. So I could previously look at maps to see, has anybody else done work in this area? Can I work off of his or her stuff? If she was out here, did she describe the units they did? So I can read what she wrote about the different units and then go and check what she described so my eye is tuned to those kind of rocks. I bring an acid bottle. It's a very weak acid. If you work in carbonate rocks like limestone, you just put a little bit of acid on, the rock fizzes, you know it's a limestone or dolomite or marble, something like that. You have to be able to write on your map, so I bring that kind of stuff. Field book or clipboard, you want to describe your units. You want to be able to write everything you see with the assumption, I will never return to this place again. You need a compass. This is a geological compass that is commonly used in the US Different countries use different types of compasses. This is a Brenton compass. So we use this to collect our data because the main thing we're trying to collect is orientations on the rocks. Cameras. If you see something special, take a picture. A hand lens. This is a hand lens. Some people call it a loop. Quite commonly, I have two of them. One's an 8x, 8 times. The other one's a 10x. So sometimes if you can't tell, you have to break the rock with a hammer. That's the next one on the list. And then do some mineral identification to describe what type of rock you have. This is really important. Igneous rocks, sedimentary rocks, actually all rocks, metamorphic rocks. When I started mapping, GPS was not big. They didn't really have many handhelds. Now GPS is absolutely essential because it gives you the exact location. When I first started mapping, you had to look at the hills and the streams and make an educated guess on where you are to place the data. GPS is essential. Smartphones. Smartphones are great. Quite often you can be in an area where you have no phone coverage, but you can still do GPS. And there's different apps on your phone that you can use. I still haven't gone to a tablet computer, but I'm trying to push our younger geologists to use it, and then they can teach me how to do it. So these are really important. This is what I take out in the field with me. So I always have all this stuff when I'm out there collecting my data. And I'm usually walking alone. There's lots of New Jersey, you don't have to worry about it, but there are other places where I wish I had somebody with me. So try and have somebody go with you. Make sure you have some sort of a medical kit. That's essential because I've had some problems where I really wish I had it. And let people know where you're going. I know now with smartphones you can trace people, but I've been up in Alaska and that was before smartphones. No one knew where I was. So safety, safety, safety. Be really cognizant of your safety and be prepared for anything. This is somebody else's field sheet, and this person actually has artistic ability. I do not. So what they're showing here is this is a stream going into a small lake, so I would assume there's a waterfall here. He's trying to show contour lines, and this is what they're mapping, a dike. A dike is an igneous intrusion into other units. So this is a close-up of what the gentleman did. He was nice enough to loan me pictures because he's actually an artist. He's really good. I try to draw pictures, but even I don't know what they are later on. So this is the type of stuff we need to create the map. And of course, we have to look at the rocks. So this is one of the few, I don't do selfies, and this is one of the few pictures of me in my master's area up in Alaska. So we want to see the rocks. And these are just typical examples. This was up in Alaska. There was a lot of cliffs, so I had a lot of exposure. This is a quarry in New Jersey, and these rocks are all basalts, the black rocks, the mouthful will come back. The black rocks are all basalts, and they're the same age as the dinosaurs. So these could be the Watchung Mountains, and the important thing is there's this red unit issue that we're trying to figure out what the red unit is doing. And once again, so here I am scale. In this quarry, there's a truck right here. That's the scale. So that gives you an idea of how high this wall is, how long this wall is. So we can use that in our understanding of the geology. Because when you're looking at rocks, you're thinking in 3 dimensions. I have this here. What's it going on? Where does this go to my right? Where does it go to my left? Where does it go behind me? Where does it go in front of me? This is fossils. This is stromatolite. This is about 500 million years old. It's blue-green algae. This was some of the earliest fossils, and it's still forming now. So these are shallow water deposits. Once again, we have one of our stellar PhD grad students in the picture to scale. You can barely see, but there's scratches going this way. You see a scratch right there. These are glacial markings. So a glacier ran over this polished it beautifully for us. So then we take students here all the time. This is another classic outcrop where the question about geological mapping is we don't have continuous geology. We're missing time. It's kind of like if your dad used to get a daily paper and he would stack it, and then somebody took some of the paper. If you wanted to go back in time, some of the papers were missing. So you would not know what happened. So what we have in this picture, we have a sandstone here, which is inclined in this direction. Okay. And below it are metamorphic rocks. Now, this is about 500 million years old. This is about 1.2 billion. Notice the hammer for scale. So that line right here is what we call an unconformity. These rocks don't match those rocks. So what that line is, it's actually 700 million years of missing newspaper. We don't know what happened between when this was formed and this was deposited. We can make a good educated guess. We can look at other areas, go to other states, see what they have. But this is quite common in geology where you have a period of time that is not represented. So you have to try and come up with things. Now, when I was making this map, this talk, somebody posted this on Twitter. And so even in Mars, this is the Curiosity rover. It's a fantastic picture. So if you look here, these layers are all fairly horizontal. These layers are all inclined. So if we track this surface like this, we're tracking an unconformity. Something happened here that created this different. Now, these could be river deposits, or these could be inclined from ripples or things like that. And this is smoother. You can see a little bit of incline here, but not as much as here. So even in other planets, we can apply our geological knowledge to understand what the geology of these planets are. And these are just more examples. This is just, once again, hammer for scale, sandstone, shale. So if I was here, I would note the sandstone. I would measure the bedding. The layers are inclined into the ridge. Okay, these are shales. So we would measure the fractures. We measure all kinds of data if we want never to go back there again. This is metamorphic rocks. My friend took this picture. And here you have faults where everything is offset. They don't match. You can see that this bed matches that bed, matches that bed, matches that bed, and I don't know where it matches over here. So these are offset, and these things happen during earthquakes. So this is showing that earthquakes happened a long time ago. And when the question becomes, well, as I said, resources, early man. So this is in the water gap, and there's a sandstone here. It's vertical. So this first formed horizontal, and then from plate tectonics, it is now vertical, and there's chert here. So early man used chert for arrowheads, for points, for all sorts of things. So when my buddies and I, we went up there and we traced this unit along this ridge, and this is what we found in one spot. These are early points. These are all in chert. This is a hammerstone. So this is what they use to pound these. And these are what we would call slugs, meaning whoever the early person was, he started to create arrow points with these units, but for some reason they didn't work out. There was a fracture. So they were left here. You can imagine whoever the person was wouldn't take a big, large rock back to camp because it's too hard. So they would work the things here and then take the best pieces with them back to camp and finish them. So this is an example before Europeans came here. I don't know, I have no idea the age of these things. That even then, the Native Americans were the early geologists tracking this bed because we found similar things in other locations on this same unit. So it was geological maps early on, resource based. I have to show you some of the locals I encountered. So once again, safety's sake, in New Jersey, I've run into bears. Usually I can see them from afar and I can avoid them. I know how to handle them. I've never been more scared in the woods than a turkey. I was stepping over a log and the turkey was sitting there and he flew right in front of me, flapping his wings. I was like a Looney Tunes person. I was up in the middle of the air with my feet moving, but I wasn't. In Africa, I ran into elephants, but I was pretty far away from them, so I didn't bother. This is a spitting cobra. I wasn't too far away from him, but I saw him and avoided it. And this baboon, several of his clan chased me out of the field. I had to run a kilometer to get away from them. And you're wondering, why do I have a jet as something I've run into? Well, I was working in Wyoming at the time, and I crested a ridge. There was a beautiful valley in front of me before another ridge. And while I was there, an F-15 flew right down the valley. I didn't know it was used for training. And I was actually above the pilot. I could look down into the cockpit. So just the fact that this jet went zooming by scared me because I wasn't expecting it, but it was also really, really neat. So go back to the new things. This is LiDAR again. So this is LiDAR shows elevation. And you can see little ridges here, which are geology. You can see a clear-cut surface here. That's a fault. Just to give you an idea, this is the Delaware River. New Jersey's on this side. Pennsylvania's on this side. So you can see that these rocks here look very different from these rocks here, and they are. These are about, I don't know, 1.2 billion. These are about 200 million years old. If we do a close-up, this is the close-up. My friend who created this is a superficial geologist, so he's looking at younger deposits, a lot of river deposits. And just by coloring elevation, we can see the lighter colors are deeper. So this is the course of the current river. And these are deposits that were laid down by the river. So at one time, this tributary probably came here, and instead it migrated. You can see a nice meander of the pool. So we can use this type of things to do detailed geological maps. And one of some other new things is this is a probe. This is a drill hole. Think of if you have a well for water. You can put this probe down. It has a camera in here. It takes a 360-degree picture of the rock. So these are actually pictures of the rock that we drilled into. So if you think of the tube from toilet paper roll, we cut it open, and that's what it looks like. And that's what this is. This is a cut open. So basically, if we were to realign this piece here touches that piece there to turn it back into a tube. So here we can match things, and we can have extreme detail on the geology. We can have orientation data, and it's just done by sticking this probe down and spending an hour or two recording the data. It's very cheap compared to an actual core. New thing is drones. Drones are becoming really big in science because they allow you to get to places we can't get to. This is a location called Pebble Bluff. It's right along the Delaware River. These are two of our stellar graduate students, and they're trying to do drones. So this is the drone. You can see it's in air. This is what they use to land it on. And that's a little closer. And basically, the drone will take a picture of this cliff. And you have to take a picture straight on, and then from on high, on bottom. And that way you get a three-dimensional image of this with orientation data, which is critical. So these are being used in, some of our students are taking this into Africa to use it on some of the mountains. I would have loved to have had this in Alaska, but it wasn't around back then. Okay, we got that. The next thing was to use seismic. This is where we send a sound source down, and the sound source goes through the bottom of the seafloor, bounces back up, and we record it. So in this picture, these lines are these lines, and they're offshore New Jersey. This is the coastal line of New Jersey. We're looking for sand resources. If you ever go to the Jersey Shore, you notice that Some years the beach is big, some years the beach is bad. And you might have heard of beach replenishment, where we put new sand on the beach. That's one of my jobs, is to find the sand that we can blow on the beach. Offshore is not sand everywhere. There's a lot of clay, which no one wants. So we go on a boat like this. This is our sound source, just like an echo, how you scream loudly, your voice goes across the valley, bounces off a ridge and comes back. That's what we're doing. This is our sound source. This is our, we call it a hydrophone, which is a water-based microphone. And that's how we collect these data. And then we can look at them and do cores, that's a core sample, to see what is the sediment type. That's our ground truth. And then we can do that. And another one, this is a little bit more, this is from work I've done. So here's Cape May. This is way up farther north. That's Atlantic City, if I'm not mistaken. No, this is Atlantic City, and this is much farther to north. The key thing to note is, notice how the colors are really thin here. The colors are thick here. Each color represents a different age. So we can tell that in the offshore, there's a huge amount of sediment being deposited here, possibly by the Hudson. And you're not really finding much down here, even though the Delaware comes out right here. So this allows us to understand how the offshore margin of New Jersey grows by just taking a boat back and forth, making sounds, and collecting the data, interpreting it, and coming up with these models. So in the end, the main thing you have to understand is, as soon as you publish your geological map, it's out of date. What I mean by that is, there's still a lot of holes where we have no data. So any geologist, using his scientific knowledge of the region and how the rocks move or change, is making his best estimate of what the geology in the covered area is. But all you need is a drill hole there, a house foundation exposing rock, and you might find out, hey, I was wrong. So that's what I mean is, it's out of date. We constantly need to update these maps with new ones. And last but not least, because we have to interpret data that we don't know, we might be making a mistake. So you can look at an old map and look at a new map and say, wow, this new map really changes the idea. And that's because we have more data. So it's really great looking at geological maps. And I've been doing it for, I'm not going to tell you how many years, but it's more than 30. And to this day, I still love doing geological maps. So that's all. Now I have to get out of here. Hope I did that right, guys. So here's now where I can answer some. Here's now where I can answer some questions. I have to first turn off my email so it doesn't keep interrupting us. So some of the question is, okay, Simon Winchester. Actually, I had this. I thought I had this. The William Strata Smith map was the first national geological map, and there's a famous book that I highly recommend reading it if you're interested, called The Map That Changed the World. Let me go to some questions here. Okay, Xavier from Sparta, New Jersey says, how long does it take for a mountain to form? I had to look this one up. And if we talk about the Himalayas, which are currently the highest mountain, and they're probably still growing. If we look at plate tectonics, which one of your previous speakers covered, the India plate originated down towards East Africa, and then through plate tectonics migrated northward before it hit the Asian plate. That impact, that collision, which led to the formation of the Himalayas, started 50 million years ago. So from beginning to current, we're talking 50 million years for the Himalayas to form. The other thing about mountains you have to understand that the only reason we have mountains is that they are uplifting faster than they are eroding away. Lynn from New Jersey asks, you can view geological maps on your own. I would recommend, if you're from New Jersey, go to the New Jersey Geological Survey. There's a website at njgeology.org. All of our geological maps are free. You can download them and look at them in your leisure. The USGS is a fantastic source for both planetary geology and worldwide geology, so I would look at those. If you're from a different state, almost every state has a geological survey. I actually live in Pennsylvania, and they have a fantastic one, and they too have all their geological maps open for the public. Okay. Surati from West Bengal in India, welcome. And it says, she has two questions. Hope it's a she. How to project the channel initiation. So she's the question here is referring to river channels, the best I can assume. So the question is, how can you find where a channel will form? And that's pretty hard on the geological map. I would say the most part is looking at low points. So geological maps, depending upon the elevation contours you have, that could be hard or it could be easy. But the channels will initiate into low points, and you can go from there, and it goes. The second question is, can you calculate erosion and deposition? You can. The best way to do it is if you have multiple years of LiDAR. LiDAR, if you have high-class LiDAR with less than a foot resolution, you can easily just subtract one years from another years, and that will give you your data. Somewhat similar to the example I was showing you in the Delaware River. Okay, some of the other maps. Okay, the earliest people, one question is from Mary, Scotch Plains. What sort of people made the earliest geological maps? Kings, explorers, landowners, business, construction, gravediggers? That's a good question. I would expect now, I don't know this, but I would expect the people who were more well off. I wouldn't say nobility. I doubt they were doing it because they were nobility. They didn't get their hands dirty. But you had to have somebody who had time to do it. So in the more distant past, a lot of the people had a day-to-day task of surviving, so they wouldn't do it. So I know a lot of pastors did it, who were interested in science, at least in the UK. They were some of the earliest mappers, shall we say. Question, do all geological maps use the metric system? No, unfortunately, a lot of US maps, we still do feet, miles, because that's what a lot of the topo map bases are that we use. Okay. Is there an instrument or software that lets you align as possible older maps? Yeah, we do a lot of what's called geographic information systems, where now with the computer and with GPS, we can take old maps and align them with our new maps. Actually, I do that all the time in my mapping, where I take my field data and bring it into a cartographic area and come up with stuff and able to map stuff. Pat wants to know if these seismic surveys are the same type that harm marine animals. Some of them, I think there's still a question about how much harm is being done. The deeper you want to penetrate, the stronger the sound source must be. The one we use in the offshore is not, as far as we know, it doesn't bother mammals, marine mammals. But we still have a rule that if you see, we can be collecting data and all of a sudden a whale will appear pretty close, and we have to stop collecting data until the whale is gone. I've had times in offshore Cape May that we were collecting data and porpoises actually follow us. So I would have to say that we're not bothering them. quite often we don't realize they're there for a while, and all of a sudden we see them, and once again, then we shut down. So Rhea's mom, as the Earth is always in motion and changing, how often are maps updated? How can you detect the changes? Maps are updated quite a bit once we have two ways. Once we have a lot more data, so we can show that there were errors from previous maps. Sometimes it's just a matter of acquiring two different maps and just looking at one to the other to see what the changes are. I did, with my state work, we made a 1 to 100,000 geological map, which was an update from the 1940 map, which was an update from the 1912 map. We've also been doing 1 to 24,000 scale maps, which are the ones I've been showing you. And so we do that as we see fit. So some of those are 60 years, 50 years between. It's just a matter of, do we have the money to do updates? Do we have a reason to do updates? Okay. Somebody named Pat actually went out in the field with my colleague Peter Sugarman, and they found, this is down in southern New Jersey, they found a green sand. And the green sand actually reacted to a Geiger counter, and that's because it has some radioactivity in it. A lot of units have very, very minor radioactivity. It's like a shale, a clay, has just a tiniest bit, nothing to worry about, but it has enough that it allows us to understand, to decipher in a well how deep, how thick is the sand, and where do we find shale, where do we find clay. Another question, are you correlating your research results with those of Rutgers scientists taking cores offshore? I've actually been involved with the research with those offshore cores. The Rutgers scientists, because actually where they did their most recent offshore cores was where I did my PhD. So they were working on that. Okay. What made you choose geology, and why did you decide to go into mapping? As I went to college wanting to be an oceanographer. I think one of our previous speakers, Ken Miller, said the same thing. Ken and I are actually about the same age. And for me, it was a Jacques Cousteau. So I wanted to become an oceanographer, not really knowing what an oceanographer was, to be honest with you. So I went to my school, and they had something called natural science. That was the oceanography. And luckily for me, that was in the geological department. So they sent me to somebody in the engineering who worked offshore, and he let me know that to be an oceanographer, you take a basic science or engineering and then just take that into the water. So I was thinking about different courses, and I seemed to like geology the best, and that's why I became a geologist. And I've always loved maps. So for me, walking in the woods, doing maps is what I've always wanted to do, and I've been lucky to do it. Yeah, so that's how I came into geology, but it's kind of like it's taken over my life, in that anywhere I go, when I go to the beach, first thing I do is walk along the beach to look at the geology, see how the beach has changed, to see if I can see different layers of sand. So that's how I became a geologist. And I must admit, I'm glad I did. And I don't see any more questions. Let me go back to that Word document to see. Is there a special name for maps that focus on tectonic plates over the history of Earth? Yes, I would call that a tectonic map. I don't know what else to call it. And those are usually very large scale maps because the tectonic plate is quite large. They can encompass both ocean crust and continental crust. So those are very, the scale of those is quite large. Are there any special museums or exhibits that focus on geological maps? I don't know. There have been some exhibits that I know of where they tried to bring geology into geological maps into modern society, meaning you can get a necktie that has a geological map on it. People have gotten tattoos of geological cross sections. There's a lot of puzzles of geological mapping. So where are areas that are not well mapped yet on Earth? I would say the areas that are harder to go to. So some deserts may be difficult. If you think about it, Antarctica is completely covered by ice, but there are some exposures, so there are some geological maps, and we can use other techniques, gravity, to understand how thick the ice is, so therefore they can kind of understand what Earth's morphology is beneath the ice. And just like a LiDAR, if there's a ridge that projects to the surface, you can make an estimate of that. So there's different maps of that nature. There's different areas. It's more, if you can get there easily, it's been mapped. If it's difficult and it takes a lot of effort, Greenland, I would imagine, would be pretty tough, once again, because of the ice. Once again, we have gravity data, which lets us know how thick the ice is. And so I think Antarctica and Greenland, they've been able to discover sub-ice lakes. Lauren, who is doing a fantastic job of running the Geological Museum, she had a period that she was able to go to Switzerland with a science team to look at how they were mapping the glacial ice. And so that's another spot that, yes, you can do glacial ice, but you may not be able to do the geology beneath it. So do we expect to make geological maps of other bodies in the solar system? Yes, we're doing it right now, as I showed you with the making geological maps of Pluto. So these are quite common. Different departments have a very good Earth and planetary science departments. So there's a lot of people. We're sending probes all the time to different planets, different moons. Some of the moons of Jupiter have very unique topography and what they're made of. So it's allowing planetary geologists to come up with different ideas. So we're constantly collecting data. Remember, even though I got my PhD at a late age, there's more science to study. We will never run out of questions that need to be studied. So if you enter into retirement and you want to study, go for it. If you're young and have questions of I've always loved planets or dinosaurs or something, these are the types of things. There will always be questions. And
Hey, Don, we have about one more question left. Time for one more question.
The one I once went for a hike. Does Rutgers offer programs for high school students where this kind of information is shared? I know that we have once again, I think Lauren and our Rhea and Julia, who are doing a fantastic job of running this whole Ask a Geologist. We have a scientific bus, I think, that goes out to different schools. I think they go out to elementary and high schools and try and bring the knowledge, try and get the students to become inquisitive enough to go out. I know I have led a field trip for undergrads who weren't geology majors, just to give them a taste of it. There are geological societies that you can join. You don't have to be a geologist. You just have to join, and they take 2-day field trips, usually locally. There's one from New Jersey, one from Pennsylvania, one from New York, one in New England, and anybody can sign up for these field trips and go on them. Is that the last question, Maria?
Yeah, I think that was all the questions you had. So thank you so much, Don, for doing this for us. That was really interesting. And thank you for everyone who tuned in today. And don't forget to tune in on next Friday. Actually, not next Friday. It's going to be the Friday after next one. So the July 24th. And at 11 a.m., we will have Michael Monzone. He is a master's student at Rutgers in the entomology department. And he is going to be speaking about invertebrate extinctions. So once again, it's not next Friday, but it is the Friday right after that on July 24th at 11 a.m. So thank you once again, Dawn, and have a great day.